Hello everyone. In this video, I will talk about stability margins, which are stability or robustness metrics that we use for analyzing the closed-loop stability of a feedback control system. We use gain and phase margins. Okay, there are also different kinds of metrics which are not very used much, so we are not cover them in this lecture. And they're very useful for both analyzing systems and design controllers. However, we need to make some assumptions. Some of them are very critical, some of them not very critical. We are just using for convenience or easily teaching the content of the course because we omitted some content from the previous parts, specifically Locus stability analysis. Okay, first of all, we assume that open loop transfer function for this system. We know that open loop transfer function is simply equal to g of s times h of s. Is a minimum phase system. Okay, in order to have a minimum phase system, we have two conditions. There shouldn't be any pole or zero in the open light plane. Okay, so this part is not allowed. But as you can see, it's okay to have poles or zeros on the image axis. That's fine. And again, open loop transfer function should satisfy this second condition, which is very trivial and almost any physical well-defined system technique satisfy the second condition. Okay, this can be a little bit like radical or technically a big assumption from your perspective. It's kind of okay because in general, physical systems like the mechanical plants or chemical plants generally fit this assumption. Not always, but most of the time, let's say majority of the plants technically satisfy this assumption. The second one is also very trivial. The feedback system should be type 0, 1, or 2. Okay, so now what does it mean? It's okay to have type 0 system, no integrator. One integrator is fine, double integrator is fine, but triple integrator is not allowed. This is also super normal. Okay, so I haven't seen any system, physical system, that is really controlled with triple integrators because it means that the system is just kind of driven by jerk without any damping or other kind of stiffness, which is also not common. Okay, so this assumption also fine. Okay, so technically, if you satisfy this assumption, okay, the second and the third one is just trivial. Okay, so the last one is really not critical. Okay, so and we added this just to ease the content. Okay, for you to better understand the phase and gain margin. Okay, keep in mind that you can still analyze gain and phase margins of the system even if your phase of the bottom plot diagram crosses the minus 180 line more than once, but you should be more careful. And in general, it is really advised to draw the Locus diagram to better understand this. Okay, so what does it mean? So let's assume that we have a Bode plot, and let's assume that we are drawing the Locus phase plot of the system. Okay, so let's assume that it looks like this. Okay, so let's change the color. And let's assume that this is our minus 130, minus 180 degree line. As you can see, it crosses this line at most once. It's okay if it never crosses this line, okay? But for this course, it should cross at most once, 0 or once. It's also not allowed from the perspective of this course if your phase plot exactly technically at some region matches the 115 plus, which means that there are infinite many intersections, which is of course not allowed. Okay, so the only thing that you should remember is we will give you systems, the plans that satisfy these assumptions. Okay, some of them are critical, some of them are just used for convenience or in order not to go deeper mathematical analysis. Okay, that's nice. So okay, that's good. So what we'll talk about this. Okay, so let's talk about first when the system breaks stability. So let's assume that we have a stable system, and at some point it will become unstable. Or sometimes we have an unstable system, we change a parameter, it will become stable. When does it happen? Okay, from the perspective of Locus, you should know that. Okay, so let's assume that we have like a triple pole system. Okay, that's nice. If I draw the Locus, okay, one pole will go there, the other two poles will do this motion. Okay, so I know that at some point the system will become unstable, and it happens when the system crosses j omega axis. So at this point, I have a gain, okay, and I know that technically poles are purely complex. I have j omega d. Okay, so which means that the characteristic equation 1 plus GOL S, okay, this is the characteristic equation, and we technically use this from Locus, has a root at the j omega axis. This is equal to 0. So we know that, okay, there exists a omega such that GOL j omega is equal to -1. Okay, so if the system breaks the stability, both in terms of from stable to unstable or unstable to stability, I know that there exists a solution omega such that G of j omega is equal to -1. So in the frequency domain analysis technique, since we are technically drawing G of j omega in terms of magnitude and phase, the goal is trying to avoid -1 as much as possible, both from phase and magnitude perspective. So by looking at the distance of G of j omega to -1, okay, so if this is a complex variable, we can talk about its phase and magnitude. We will technically quantize the gain and phase margin, and it will give you how stable or how unstable the system is. Okay, so what is gain margin? Okay, so the gain margin is more intuitive, but it is slightly less useful. We will generally use phase margin to design controllers, but it's also important. Gain margin is the change in the open loop gain. Okay, so we introduce a fictitious kappa or k to the system. Okay, it's a gain required to reach the stability limit. Okay, so this is not the part of the controller. We technically assume that we know G, we know H. Okay, but there is some sort of uncertainty in the system. So because this is error, okay, error signal, and we just feed the error signal to the controller, sometimes we have some measurement error, or sometimes the case here, when we are supplying the torque or input to the system, there is some sort of amplification error. So we are trying to analyze when the system breaks its stability while changing the gain. Okay, from the perspective of Locus, it is very easy. Okay, so I will solve an example here. And from the perspective of, again, frequency domain or Bode plot, it's also relatively easy. Okay, so let's look at this from the perspective of Locus. Okay, if I know G, if I know H, okay, and if this is my system, okay, together with the controller, what I can do is I can draw a Locus with respect to kappa, and you should note the fact that kappa is equal to 1 is the nominal gain. Okay, it's not 0, it's the kappa, because I already designed my controllers. Let's assume that I have something like this. Okay, I have double pole here. Okay, so this goes like this. I'm not sure, which is quite possible to have a root looks like this. I should have a pole here also, and also this goes like this. Okay, that's great. Okay, so the change in open loop gain, and we look at the change with respect to the perspective of the nominal gain required to reach the stability limit. Let's assume that when k is equal, let's change the color also. Okay, that's great. So when k is equal to 1, okay, our system is here. Okay, closed loop paths are here. This is k is equal to 1. Okay, and I know that if I increase my gain at some point, I will break the stability barrier, which is here. Okay, and this is critical gain, kg. This is kg, and the gain margin, from the perspective of root locus, is technically equal to this value. Okay, so gain margin is equal to kg divided by k nominal. We know that k nominal is equal to 1, so it's simply equal to kg. Okay, this is my gain margin in terms of absolute units. Okay, so this is a magnitude. And if you remember, in the Bode plot, we converted magnitudes to a specific decibel units. We can do the same thing for the gain margin, such that gain margin in decibel units is equal to -20, okay, log gain margin. That's it. Okay, that's really great. Gain margin. If you compute the gain margin, you can technically take its logarithm with respect to base 10. Okay, don't forget it's base 10 multiplied with, it's not minus, sorry for that. It is just 20. 20 log 10 gain margin is the gain margin in decibel units. This is unit, this is just magnitude, okay? And this has a unit. Okay, so if I give you root locus, you can compute gain margin. Okay. So how do we compute the gain margin? Using the frequency response data. Okay, good. So first of all, let's look at this. So at this point, okay, so we use its gain, right? We know that G, okay, G of OLS has a solution, right? Okay, J omega, okay, is equal to minus 1. Okay, or it's equal to, yes, exactly, this should be equal to minus 1. Okay, that's great, because we already know, no, it's not minus 1, sorry for that. Okay, it's minus 1, no problem. Okay, that's nice. So what I can do is, from the Bode plot perspective, if I look at its phase, G of, okay, G of J, let's say omega critical, okay, is equal to minus 1. If I look at its phase of G of J omega C is equal to minus 150 degrees, or you can say 150 degrees. So at this specific point, I have an omega C such that my frequency or phase should be equal to minus 180 degrees. Okay, so what is K at this point? We know that Kg is equal to 1 over, from the magnitude condition of the root locus, GOL J omega G. Okay, so if I use this, if I find this frequency, which is called phase crossover frequency, and if I compute this quantity, gain margin in classical units or normal units is equal to GOL J omega phase crossover frequency, or in the decibel units, it's equal to minus 20 times log to the base 10 GOL J omega phase crossover frequency. Okay, so from this perspective, the good thing is, first of all, you don't need to draw Bode plot of the system in order to compute this. Okay, so what you will do is, you have G of J S, you will just plug S with J of J omega, you will find a root for omega. Okay, when you find omega, you will plug it and you can compute the gain margin quite easily. However, if you are given a Bode plot, the story is much easier. It's super easy. Okay, so what are we going to do is, I will sketch it quick, then we will solve an example. Okay, so let's have a phase plot and let's have a magnitude plot. Okay, that's it, or something. We don't need to do that. Okay, so, and let's assume that our phase looks like this. Okay, whoops, that's great. And this is my minus 180 degrees. So you can find the phase crossover frequency. Okay, and let's assume that this is my 0 dB line. So what is 0 dB? Okay, so when we look at the gain margin, okay, so this is my 0 dB line, 20 log 1. If it is 1, if my gain margin is 1, okay, my gain margin is equal to 1, okay, because it's equal to nominal value, okay, so it is like the 0 dB point. Okay, so if it crosses, for example, if my magnitude crosses 0 dB line, it means that I'm exactly on the imaginary axis, because my nominal gain is satisfying the equation, which means that I'm on the imaginary axis, so I want to avoid the 0 dB line. So what we will do is, we will try to look at the distance to the 0 dB line. And let's assume that my Bode plot normally looks like this. Okay, this is one possibility. Or another possibility, let's look at this. Okay, so this is another possibility. it's exactly crossing the 0 dB line, and this is another possibility. Let's look at this. Okay, that's great. So we can do that. So what I can do is I can look at the gain. Okay, so let's look at the first one. Okay, my gain is negative. Okay, but it's logarithmic scale. Okay, it's negative. It's logarithmic scale. So it means that my current gain is less than the critical gain, because critical gain when I crosses the 0 dB line. Okay, that's nice. So which means that I'm stable. If this phase crossover frequency gain is technically crossing exactly the 0 dB line and exactly on the critical line, and the system is currently unstable and the margin stable, and if I am here, it means that I'm already past the critical gain. I'm above 0 dB line. It means that I'm unstable, which means that I'm technically in the unstable region from the perspective of the Locus. Okay, so how we compute the gain margin? Since Bode plot is already giving you the gain margin in the dB scales, what you do is you measure this distance, and this is your gain margin. Okay, now let's look at the formulas, and you will see better understand the result. Okay, so this is my gain margin. Okay, I already computed that. Okay, so first, so sorry for that. We need to compute the phase crossover frequency. We can do it either just by hand, or we can look at the Bode plot. Okay, that's great. And then using the phase crossover frequency, if we are giving the open loop transfer function, we can compute the gain margin in classical units, and we can convert it to gain decibel units, which is equal to minus 20 log 10 GOLF J omega phase crossover frequency. Okay, so this is the gain of the system at the phase over frequency. So this is the scale, as you can see, and it's minus. So our gain in decibel units is minus here, and since I'm looking at the difference with respect to the 0 dB, another minus makes it a positive gain margin. Okay, so in order to have a positive gain margin, which technically says that it is potentially a stable system, my gain at the phase over frequency should be below the 0 dB line. Okay, this is the whole point of the gain margin, and you will better understand the whole concept with this example. Okay, that's great. So this is an example, and open loop transfer function of the system is given as 3 divided by s plus 1 squared. Okay, so I have root locus and I have Bode plot. Okay, so let's look at the root locus. So for in this root locus, k is equal to 1 is located somewhere here. Okay, so I don't know exactly. And we know that it is stable, right? Okay, so it is discretely stable, but gain margin is technically measuring what is our margin of stability, or what amount I can increase the gain and I will be still stable. It's an important margin, and technically, if you don't label this k on the root locus doesn't give you this important metric. It's a different metric than, for example, looking at the distance with respect to the imaginary axis, which gives you settling time, which is important, but it's also important to measure the margin of error in terms of increasing the gain such that I'm still stable. So, okay, this is my critical case. So my gain margin is technically equal to 2.67. Okay, so if I compute the gain margin in decibel units, I need to compute 20 log 10, okay, GM, and if you compute that, you will see that it is equal to 8.52 decibels, so it will be very close to that. Okay, so you can compute the gain margin from the root locus. Okay, it's important. It's one of the things that is common in the root locus and the Bode plot, but this is not true for the phase margin. Okay, so we computed the gain margin, that's great, from the root locus. Now compute it from the Bode plot. Okay, so gain margin decibel units is equal to 8.52 decibels, or in the normal units, it's equal to 2.67. Okay, that's nice. That's nice. Okay, so what we do is we compute phase crossover frequency. So phase crossover frequency is the frequency when my phase plot crosses the minus 180 degree line, which is happening right here. Okay, so and if I look at this frequency, okay, it is equal to 1.73 per second. And if you look at this from the perspective root locus, it is actually equal to the y-axis of the geometric crossing. So this is equal to 1.73 j, or this is equal to minus 1.73 j, because it is the frequency where the technically stability boundary crossing is happening. Okay, this is actually natural frequency of oscillations or natural frequency of the system. Okay, so we computed, or we didn't compute, we just look at the frequency gain crossover, or phase crossover frequency from the Bode plot, and it's equal to 1.73 radians per second, and we verified it from the root locus. Okay, then what you do is you look at this gain here, okay, and this gain is equal to minus 8.52 decibels. Okay, so it means that I'm below the critical line, which is 0 dB line. That's really important, which means that I'm stable. So this distance, okay, so distance this from the 0 dB line is equal to 8.52 decibels, which means that my gain margin is larger than 1, which is a good thing, provided that my phase margin is also larger than 0. Okay, good. That's nice. So the first necessary but not sufficient condition for stability is gain margin in decibel units should be larger than 0, or gain margin in classical units or non-decibel units should be larger than 1. This is a necessary but not sufficient condition. Okay, in order to satisfy sufficiency, we need to also look at the phase margin. As you can see, it's 42 degrees, which is larger than 0. So it is a stable system. But let's talk about the phase margin. Now we will talk about the phase margin. Okay, so unlike gain margin, there is no easy way of technically understanding a phase margin from the root locus plot. So I will directly talk about from the perspective of transfer function and the Bode plot. Okay, so in the phase margin computation, the problem is this. What is the amount of phase lag required to reach the stability limit? So what is phase lag? So let's assume that we have an experiment where we can add a fictitious artificial phase lag to the system. Okay, so it's a complex quantity. As you can see, we cannot do in a real system, but you can think as you add a filter, low pass filter, which can technically affect the phase of the system without changing the magnitude much. So you can think it from this perspective. Okay, or you can add a delay, which only introduces the phase of the system, but it doesn't change its magnitude. Okay, so what's the maximum amount of phi m such that the system will still stay in a stable region, or when we pass a critical phi such that the system becomes marginal stable? That's the whole point. Okay, so let's remember the original characteristic equation. So this is our characteristic equation: 1 plus GOL S is equal to 0, and for each S that satisfies this equation, we have a pole of the system. Okay, so what we do is I add a phase to the system, 1 plus e to power minus j phi. Okay, it's a complex quantity. It has a magnitude of 1, but it has a phase lag to the system. GOL S is equal to 0. Okay, that's nice. And if the system passes a critical stability limit, I know that it has a root on imaginary axis. So 1 plus e to the power minus j5 GOL j omega, and we call it gain crossover frequency. I will call it, you'll understand later. Okay, let's say G is equal to 0. Okay, so for at this critical phase, my equation is this: e to power minus j phi m GOL j omega g is equal to minus 1. Okay, so I have a complex quantity. It's equal to minus 1. It has a magnitude and it's a phase. If I look at the magnitude, so magnitude of e to power minus j phi is equal to 1. So I need to satisfy this equation: GOL j omega g is equal to 1. So at this specific frequency, when I'm computing the phase margin, my gain, the magnitude of g of j omega should be equal to 1. And if technically I draw it from the Bode plot, this is technically the point where the magnitude plot crosses the 0 dB line, because my magnitude is equal to 1. Okay, because we know that 20 log 10 times 1 is equal to 0. Okay, this side. So this is called gain crossover frequency. So if I look at the phase, okay, and technically compute the phase of this equation, I will technically compute that phase margin is simply equal to, since it's minus 1, it is 180 degrees. Okay, this guy. It's also possible to say minus 180 degrees, but this is more convenient, plus phase of GOL J omega G. Okay, so in order to compute the phase margin of the system, what you do is you technically first compute the gain crossover frequency and compute the phase at this point, and phase margin is equal to 180 degrees plus the phase of the system at this specific frequency. So this is the formula. Actually, technically computing this from the Bode plot is super easy. Okay, it's much easier than just computing it by hand or showing it technically on the slide. Okay, so let's go back to our original problem. Okay, so this is the same thing. So this is the gain crossover frequency. Okay, how you can compute it directly using the Cartesian units. In the decibel units, it corresponds to the point where my magnitude plot crosses the 0 dB line, and my phase crossover frequency is this. Okay, so what I do is the same thing. I look at the 0 dB line, okay, and I look at the intersection, which is here. So this frequency, if you look at from the MATLAB Bode plot, corresponds to the frequency of 1.04 radian per second. It's approximately equal to 1. And in the midterm, if it's perfect, fine. If you just put 1 radian per second, that's fine from the Bode plot perspective. Okay, so we look at this frequency, and I look at the phase at this frequency, which is approximately equal to minus 135 degrees. It's a little bit below that. I think minus 130, I don't know, 3 degrees. Okay, so my phase is at this point is equal to minus 133 degrees or something like that. So what is my phase margin? Phase margin is equal to 180 degrees minus 132 degrees. It's my phase margin. But from the graphical perspective, it's even easier. The phase margin is this difference. Okay, I'll look at my critical line. My 180 degrees is critical line, and this is my positive phase margin. Okay, and if you remember, my gain margin was positive. It was greater than 0. My phase margin is also positive. It's greater than 0, which means that the system is stable. Okay, that's nice. So let's assume that I change the gain without changing the phase, and I can do it just technically changing the Bode plot. Okay, so if I add a gain, and if I technically increase the Bode plot, and let's assume that I shift the magnitude plot to somewhere this. Okay, I can do that. Or let's make it worse. I shift it such that it crosses the 0 dB line here. Okay, and if I look at the phase, I'm just increasing the gain. Okay, so I adding a gain to the system. Okay, and as you can see now, it crosses a phase approximately minus 225 degrees. And if I look compute the phase margin, it will have a different direction. Okay, now this direction is not preserved, so my phase margin will be now it's equal to minus 45 degrees, which is negative phase margin. Negative phase margin means that the system is unstable. Okay, so phase margin, if it's positive, measures how robust, stable the system is, or if it's unstable, how far we are away from the stable region. It really measures relative stability with respect to the critical stability limits. And always remember that critical stability condition corresponds to the point where Bode plot, the magnitude plot crosses the 0 dB line, or the phase plot crosses the minus 180 degree line in the phase plot. Okay, now what are we going to do is we will solve some examples regarding both the plots and phase and gain margins, and later we will learn designing controllers using phase and gain margin. They will call phase, lead, and lag controllers. Okay, so this is a system, and we already computed the phase and gain margin of the system using Nike's plot. Now the goal is doing it with the Bode plot. Okay, so I already drew the Bode plot for you, and these are actual Bode plots, not the approximate ones. And let's look at the gain margin. Okay, so what's the gain margin? I need to look at the point where my gain is crossing minus 180 degrees. Okay, let's change the color. Okay, but it's never crossing minus 180 degrees because if you remember, the polar plot is like this for the system. Okay, and no matter what I do, it never crossing the negative real axis. So gain margin is infinity for the system, and it's also infinity in decibels case. It's good. So gain margin is infinity. Okay, we are done with that. There's no problem. We like this. Now what we need to do is compute the phase margin. Okay, so let's find our ruler. Okay, and let's start with k is equal to 2. When k is equal to 2 is crossing the 0 dB unit, it's exactly when frequency is equal to 1 radian per second. The phase at this point is equal to minus 90 degrees. Okay, so what is phase margin? In order to compute phase margin, I need to find this length in phase, which is exactly equal to 90 degrees. It's nice, right? It's relatively easy to compute that. Okay, let's do the same thing for the other gain. So let's put a ruler. Okay, so it is, I think, exactly here, and I know that's exactly here. So the phase at this point is equal to minus 120 degrees. So if I look at this distance, I can compute the phase margin as 60 degrees.